The
Okay.
next talk will be given by Michel Bergmann from Inria and Bordeaux University on POD-assisted computations of incompressible fluid flows, applications to wind and marine energy. Thank you, Michel. Take it away.
Okay, thank you, Troyan. So this talk has been performed here in Bordeaux in the Memphis team at Inria. So I will firstly show you some Memphis activities on renewable energy. So Memphis team is myself, Afaf Bouargan, and Angelo and Thomas. Well, I guess you all know Angelo and Thomas. And so we have application in wind and sea wave energy. And I will show you how possibly to use POD reduced on a model for these kinds of application. But this talk will focus basically on the improvement of the POD subspace robustness with respect to some input parameters. And I will show you a way to sample the input parameter space in the solution space using some principal angles or the geodesic on the Grassmann manifold. And I will also introduce a new metric, and then I will conclude with the conclusion and perspectives. So we have different kind of collaborations. So we have a collaboration, and we have a collaboration with Valorem. It started 12 years ago, and we had 2 industrial PhD students with them. So Xin has developed a kind of reduced order model, is an actuator disk for the blade optimization. And Claire Taymans has developed Navier-Stokes solver on the Octree. And we had also interaction with Valorem in the previous European project, Aerogust, and now it continues in the Aria project. Okay, for the wind energy, another application is with IFPEN, so the French National Institute for Petroleum and Renewable Energy. And you can see on this picture, so very large wind turbines. And we have 2 projects with IFPEN. So the first one is to study the aeroelastic effects at the end of the blade, because they are very large, something like 2,000 to 2,050 meters diameters, so very large wind turbines. So this is the thesis of Caroline. And we have also a postdoc, Nishan Kumar, and Nishan is interested into a wind farm. How can it be possible to perform numerical simulation or numerical prediction on a wind turbine farm? So he will use data-driven machine learning techniques for the wind farm, and actually by coupling the actuator lines using SOFA. So SOFA is developed on OpenFOAM with data-driven machine learning for the wake. Another kind of application is with the Politecnico di Torino. So another application, this is marine energy, sea wave energy here. And so this collaboration that started 7 years ago, and now we have a PhD student, Beatrice, and Beatrice will study multi-fidelity and multi-scale numerical modeling of wave energy converters farm. And the idea is to couple a full order model here, star CCM plus, with a POD reduced order model. And we also plan to have secondment at Optimal, probably to try to use OpenFOAM instead using star CCM plus. And finally, the last application we have on wave energy is with the Région Nouvelle-Aquitaine. So Région Nouvelle-Aquitaine is here around Bordeaux. And we have also a postdoc here, and the goal is also to develop a multi-fidelity approach and multi-scale numerical modeling of wave energy converters, but in a kind of different philosophy. So the idea is to couple a full order model, let's say the Navier-Stokes equation, but with asymptotic reduced order model, like shallow water equation or Boussinesq, these kind of things. Okay, that's for the picture just here. So you may notice in the previous slide that the full order models are almost never used alone for wind or marine energy applications. So because it requires very large CPU cost, multi-scale problem, and also for the optimization where you have to solve several times the state problem. Okay, so we use simplified models. So we use like asymptotic reduced order model, like shallow water equation, or we also use implicit incompressible Navier-Stokes equation. We can also use simplified numerical model based on data, where we use only the polar curves for 2D airfoil. So, and the blades are actually modeled using extra volume forces in the equation, and we can use actuator disk or actuator lines. And in this talk, I will focus onto the model order reduction based on data using the primitive variables. And we will use the proper orthogonal decomposition because we have two projects on that with IFPEN and with the Politecnico di Torino. So just several questions here and remarks. So the question is it possible or is it accurate to use a single POD reduced order model into the whole computational model? And in other words, is the same accuracy necessary into the whole domain? And a few years ago, we write a paper with Optimad also, and we observe that it is quite obvious that we observe that large POD projection errors are in the vicinity of the obstacles and low POD projection errors elsewhere. So the proper solution is to try to couple the full order model in the vicinity of the obstacle with a POD reduced order model elsewhere. So this is the general configuration. You can imagine here, this is just the example. This is an airfoil, and you may know that if you want to perform numerical simulation of a flow around this kind of airfoil, you need a very large computational domain to avoid reflection due to a boundary condition. So the idea is to try to only use full order model in the vicinity of the obstacle and a POD reduced order model elsewhere with an overlapping zone here. So it can be viewed like the POD give boundary condition to the CFD and CFD give conditions to the POD, and the POD can be viewed as a propagation model. So you can imagine maybe another airfoil here. So the POD is really a propagation model that propagates the information, the vortex, and everything. But the main question is how to compute an appropriate and robust POD subspace for the input parameter space. Because here we have one airfoil, but you can imagine another airfoil, a cylinder, something else. So you need a reduced order model that is robust with respect to this input parameter space. So just a few words about the proper orthogonal decomposition, because I imagine everyone know a little bit about proper orthogonal decomposition. So it has been introduced in the context of the fluid mechanics and the turbulence by Lumley in the 60s. And you have flow realization here, the square, and you look for the direction that on the closest in an average sense to this realization. So the POD basis solution of this maximization problem, and you can demonstrate that this problem is equivalent to a Fredholm equation. And here we use the snapshot method introduced by Sirovic that consists to perform correlation in time and average in space. So we can compute phi, and so any field, let's say the velocity fields here, can be decomposed onto this basis. And now we have to find this temporal coefficient. So there's two ways to do that: an offline, let's say offline or online reduced order model computation. So what I talked about offline is a Galerkin or Petrov-Galerkin reduced order model. So we use that decomposition. So UG here can be whatever you want. It can be zero, the mean field, or something else. So you take that expansion, you put it in the Navier-Stokes equation, in this case, perform Galerkin projection, and you obtain this kind of dynamical system. And this system is simple to solve, but instability usually occurs due to some numerical dissipation. And so you need a closure model. So it can be functional, structural, whatever, but you need a closure model. And now a different strategy is to use an online reduced order model. So this is a Galerkin-free reduced order model. So now we have a decomposition for velocity and for the pressure. And now the goal is to find this coefficient. And this coefficient are obtained minimizing the differences between the high fidelity solution and the POD solution. And this reduced order model is finally more stable than a classical Galerkin projection, since we have high fidelity information that are involved. But once again, in any case, an adaptive POD subspace is required. So just a few works we did in the last year. So the first one is in Optimad. Also, this strategy, high order model inside this square and a POD reduced order model elsewhere. This is the same here. This is done by Optimad. More recently, we do also something similar with Stanford. Okay, now a robust POD subspace is required. So the main question is how to perform an efficient sampling of the input parameter space. In the previous study, we just perform a uniform sampling in a Cartesian way because it is very simple. But of course, it's not optimal. So the distance in the parameter space is not equivalent to the distance in the solution space. And we also propose different kind of sampling strategy based on something like adaptive mesh refinement. But today, I will talk about a new iterative sampling based on the distance criterion, and this distance in the solution space. So for steady problem, it's quite easy to compute the distance between solution for steady case. You can imagine computing the Wasserstein distance or something else, the relative difference or errors. But for the unsteady problem, it's a little bit more complicated because you can have a set of snapshots for one POD for one solution, and for another operating condition, you can have another set of snapshot, and so it is difficult because there's no bijection between snapshots. So it's easier to compute the distance between subspaces spanned by the solution, and we will use POD bases for different operating conditions. And we will do this using the geodesic and the Grassmann manifold or the principal angles with other metrics. So just in few words, so this is the principal angle. You can compute the angles between subspaces here. And this is equivalent to the geodesic and the Grassmann manifold. So I will give more information in 1 minute. And then we want to perform interpolation. But if we want to interpolate the solution, we have to be sure that the solution to be interpolated is on the geodesic, okay? And so that's why the interpolation should be performed using quite close points. So the principal angle is quite simple. So you can consider you have two subspaces, and you look for the direction in the first that is the most correlated to another direction into the second, and you compute the angle between these two directions. Then you remove that direction and you do the same with the remaining information. So that's the principal angle. And you can define different metrics from these angles. And this matrix actually is the Grassmann distance. It is equivalent to the following one, that is the geodesic and the Grassmann manifold. So the Grassmann manifold is a manifold generated spanned by some subspaces. And here we consider the n-phi dimensional subspace. N-phi is the number of modes, POD modes you consider, of R and F. So NF is the number of discretization points. And it can be viewed as a point onto the Grassmann manifold. So if you have points, you can compute distance between points. And this can be done using SVD. And then you can also perform interpolation between more than two subspaces. So, yeah, I didn't say that, but for the principal angles, you can perform only interpolation between two subspaces, but with different size. And with a Grassmann manifold, you can perform interpolation between more than 2 points, but for the same size of the POD basis. So this is the first example. So we want to predict the flow characteristics for very simple example, cylinder, wake flow, laminar between 100 and 500. So I want to perform a sampling of that. So I start with these 2 points, 100 and 500. So without any information, or I add a point into the middle of this interval. Okay, and this is this Reynolds number. And this is the distance between these two Reynolds number and the distance between these two Reynolds number. Okay, now I continue the process. I add a point onto the larger distance. Okay, a new one. And you can see that the total distance here computed by continuation is becoming almost stationary, right? So meaning that now if I add the point, it is almost onto the geodesic. And since it is onto the geodesic, I can interpolate it, and it's not necessary to compute a new high fidelity simulation. And to interpolate between 2 points on the Grassmann manifold, so onto point S0 and S1, the interpolation is performed into the tangent space to the Grassmann manifold that is here, and you can compute the direction onto that tangent space. And this is the initial condition. And then if you want to perform interpolation here for periodic basis between S0 and S1, you just replace S by the desired value. And you obtain an interpolated periodic basis here. And this is the errors. So the dot line is the minimal error I can obtain. Let's consider this interval. Okay, the blue line is the error if I only consider the periodic basis here at the left corner, and the green is the error with this periodic basis, so it's not that good, of course. And the red line is the error obtained by a mixed periodic basis. And mixed periodic basis is that I take the snapshot here, take the snapshot here, and compute a periodic basis with the same number of modes, of course. And this is in black, the error obtained by the Grassmann interpolation. And you can see that in this case, it's quite efficient, right? So now a more complex case, not that complex, but with an input, two-dimensional input parameter space. This is a pitching airfoil with amplitude and frequency. Okay, so I guess I can skip that. So the question is about the choice of the matrix. I will show you that it influences the results, and also the grid of the sampling convergence. So in the previous case, so I have a reference that is the sum of all the distance between points. Okay. Now here in 2D, it's a little bit more complicated, and I will consider the sum of all triangle surface, but the surface computed using the distance in the solution space. Okay, this is the simulation, and you can see that the flow is really different for every operating point. And this one is a little bit strange. It's not a computation errors. This is really something that is physical. You can see a dissymmetry of the wake. So if I will perform the sampling, I expect to have a lot of points near this point. Okay, so now I have computed a lot of numerical simulations here. And now for the sampling, I will move to the closest point. I will not compute another points because I have a lot of points. So I will only move on that lattice. Okay, so I start with the triangulation here as the reference, as I said, is I compute the sum of the surface of all the triangles, but the distance here is taken in the solution space. Okay. So this is the drag coefficient, the trust effect, just to show you that the solution varies a lot in this region, right? And it is quite smooth here. So if I perform a sampling, I would expect to have a lot of points here. And this is with a Grassmann distance, and you can see it's really not good. But this is not what I expected. And you have a very slow convergence here. And this is due to the fact that the Grassmann distance or the principal angle consider all direction with the same weights. And the question is, does it matter if the principal angle between higher order modes is near p/2? So actually the principal angle or the geodesic on the Grassmann manifold mostly consider the dissimilarities between subspaces than similarities. So the distance, as you can see here, is increases with the number of modes. So it's not really what I wanted. So since we are considering the distance between bases, that it is PUD basis, so we have information about the energy of the modes. So here, when we compute the correlation, the principal angles of the correlation between this one and this one, we can compute the coefficient y, solving this linear system. and then we can give weights. So lambda is the eigenvalue of the POD. This is for the first operating condition, second operating condition, and I just take an average here and put the weights in that energy weighted distance. And now if I plot this error with respect to the number of modes, you can see that after a while, it is almost constant. And this is nice, okay? So now if I perform the sampling with this metric, you can see we can obtain exactly what we want to obtain. A lot of points here, okay? And we can give a threshold and start when we want, okay? And it does not depend on the number of modes. So it seems to be good. So let's consider this triangle and see interpolation on that triangle here. So to perform an interpolation in a 2D parameter space, so we can do this with a Grassmann on the Grassmann manifold. So we have two directions here. We can start from one point. We can go to this one. We can go to this one thanks to this direction. And we can also compute a mixed direction here in between. And this parameter alpha and beta can be computed in classically in the parameter space. And you can obtain that direction and move along that direction, okay? So basically we can interpolate between more than 2 points. And this is the error, projection error. If I consider 3 modes or 21 modes, if I consider only the bases here, now only the bases on these points, now only the bases on these points. What is more interesting is a mixed POD basis. Once again, I consider snapshots here, here, here. I compute a POD with all that snapshots, okay? And you can see here that the error is 3.5 and 2.0. And if I perform here Grassmann interpolation, so it's a little bit better here, but worse here. Okay, so potential sources of errors here is that after a while, the maximal angles are, at least for high frequency modes, probably are near p/2. So meaning that instead of performing the interpolation in that direction, you can perform interpolation in the other direction, you obtain something that is totally wrong. And also the computation of the direction here, gamma I from alpha and beta is not adapted to a solution space. And also the computation of S along that direction may be not adapted to. This is a simple example. Let's say you consider parameter mu1 and mu2, and you want a parameter in the middle of the interval. So you choose this interval in the parameter space, go onto the Grassmann geodesic, and you can see here that you are not in the middle on this manifold, okay? So the idea is to try to approximate the manifold for nonlinear interpolation. So what we are doing here is, this is just an example, we consider all these points, but instead using the distance matrix computing, for instance, if we consider this point and this point, computing the distance between this and this, we can compute the shortest path on this graph here, okay? So this is called an isomap. And then after we compute a new distance as being the shortest path onto this graph, we can apply classical multidimensional scaling, an Euclidean embedded of this point to have a representation of the manifold. And this is an example. So, okay, this is the original matrix. You can see that you have, this is the eigenvalue. So basically there's nothing here. We can say anything about that. But if we use the modified matrix, you can see that we have a large decrease here in the eigenvalues, and you can represent here, give a representation of the manifold. This is in 2D, in 3D. So if we consider the 3D problem, you have this representation, you can see, and probably this can give you some constraint to perform a nonlinear interpolation, or at least to improve your interpolation. Okay, so I don't know how many time left. So just I jump to 2 minutes. Okay,
something like this. That
so
2-3 minutes, maybe 2-3 minutes.
Okay. So this is just a summary of what we did. So in the future, we want to dig a little bit this manifold approximation via Grassmann and the multidimensional scaling. And also we are studying something a little bit different using response surfaces from active subspaces or active manifolds. And we have a PhD student of the active subspace, and we have also discussed a lot with Optimal about that. And so now, if we want to perform multi-fidelity numerical modeling for the wave energy problem, we actually have some problems. So for the wind turbine, the problem is that the PUD reduced order model, since it is a propagation model that gives information, let's say, to the wind turbine, it has to contain some turbulences, right? And you can see here, this is the, I'm sorry, I just go back. This is done by Nishan Kumar, the postdoc with IFPEN, and you can see here with 40 modes. So this is only 70% of the energy, but you can see the differences here. You have a lot of, let's say, turbulence here, okay? And we need that. So we have to develop a strategy. So how to pick and keep some higher mode, but on low energetic. We can think about different criteria like entropy or things like that, or add synthetic, let's say, universal modes in the PUD expansion. And we have also problem, we have a lot of problems actually. We have problems for the wave energy converters, because if we want to use PUD for B-fluid configuration, this is not easy because actually you have a moving front here. And the linear affine approximation is not adapted to represent something that is non-linear. So we have developed different strategies, or we are developing strategies. So the first one is the snapshot clustering, so, and then perform a PUD on that cluster. So we have, in some sense, a piecewise linear interpolation. And another way is to perform a mapping of the snapshot, so map onto a reference configuration, and then perform a PUD to obtain something that is non-linear, I would say. And we can use optimal transport. And we can also use something developed recently in Stanford. It's a quadratic approximation. And yeah.
Very nice. Thank you. Thank you, Michel. That was a very nice talk. Thank you.
Thank you.
Beautiful. Any questions? So actually we have about two minutes. So we started a little bit late. This we're a little bit late, but that's okay. So everyone's gonna get any questions, please unmute yourselves and ask the question for Michel. Maybe one or two quick questions. If not, I don't see any raised hands. I have a quick question for you. So can you explain? Very nice. I mean, so can you explain a little bit the idea between the POD weighting of the basis function? So you explained it, but I
okay. I can go back on that. Okay, this one. Okay.
Yes.
Because if you consider two bases without any knowledge of the importance of each mode, you can compute the principal angles. But here we are considering proper orthogonal decomposition basis, right? So we know that each mode has not the same influence at the end. So when I compute the most correlating mode here, so this is the decomposition, the PUD decomposition, I can compute this parameter. So let's say Y have a large contribution of the mean flow, so the most energetic flow. So let's say, for instance, 1, 0, 0, 0, 0. I can add a weight here that is the eigenvalue of this PUD basis. That is very large here. So it gives you a large weight here. And on the contrary, if you have, let's say, a low energetic mode with a very small eigenvalue, it will not influence this distance. That's the story.
Very good. Thank you. Thank you, Michel.
Okay.
Any questions? Any other questions, maybe? No? Okay. Well, let's thank Michel again for a very nice talk. Thank you, Michel.
Thank you.